Our today's presentation aims at describing a rapid and simple approach to assess the multi-axial fatigue life in notched components based on the total strain energy density. This is the agenda. Firstly, the motivation and goals, then a brief overview of the multi-axial fatigue life prediction model. After that, experimental and numerical procedures. Next, results presentation, and finally, some concluding remarks. Advanced engineering components, due to the combination of geometric discontinuities and complex loading, are prone to fatigue failure. Thus, the development of durable and reliable products requires not only full understanding of the entire fatigue process at the critical regions, but also accurate fatigue life prediction models. Under multi-axial loading histories, fatigue design is a very challenging problem. Briefly, multi-axial fatigue models can be organized into stress-based, strain-based, and energy-based approaches. Regarding the notch effect, it is generally accounted for using the theory of critical distances, the strain energy density concept, or fracture mechanics. The most sophisticated models require extensive experimental programs and complex computational simulations, which can make the process too expensive and time-consuming in most cases. Our proposal aims to solve these drawbacks. We propose a simpler approach based on the total strain energy density concept that allows a rapid fatigue life evaluation from a limited number of tests, more specifically, 2 tests. The model is based on 2 premises. 1. Smooth and notched samples accumulate the same damage and have the same lives if the stress-strain histories at the initiation sites are identical. And 2. Fatigue failure occurs when the total strain energy density at the initiation site reaches a critical value. The modus operandi consists of 2 main steps. Firstly, we develop a fatigue master curve. In the current formulation, the amount of experimental data is limited to 2 low-cycle fatigue tests performed at 2 strain amplitudes. These tests allow the development of the strain-life relationships and the development of 2 single-element numerical models, representative of the cyclic plastic behavior. By combining the experimental data and the numerical models, we define a fatigue master curve relating the total strain energy density with the number of cycles to failure. Here, the total strain energy density is accounted for by the sum of both the elastic positive and the plastic components. The second stage deals with the multi-axial fatigue life assessment of the notched components. Here, we determine an effective value of the total strain energy density at the critical region by applying the theory of critical distances, which is used to estimate the number of cycles to crack initiation. In order to test the model, some experimental work is needed. We have conducted monotonic tensile tests, resonant tests to evaluate the elastic constants, and low-cycle fatigue tests to determine the cyclic plastic behavior. The material selected was the 34 chromium nickel molybdenum 6 high-strength steel. After that, we have performed multi-axial fatigue tests under different loading scenarios using cylindrical specimens with U-shaped notches. The loading scenarios comprised of 2 bending torsion ratios, more specifically B equal to 2T and B equal to T, and 3 orientations of the bending moment with respect to the notch root, namely 0 degrees, 45 degrees, and 90 degrees. For each case, at least 3 stress levels were considered. The tests were conducted under pulsating loading conditions. Regarding the numerical procedure, firstly we developed 2 single-element models representative of the cyclic elastic plastic behavior of the material. The models assume 2 main features. 1. The isotropic elastic behavior was modeled by the generalized Hooke's law. And 2. The plastic behavior was modeled by the von Mises yield criterion, coupled with the Lemaitre-Chaboch nonlinear kinematic hardening law under an associated flow rule. The von Mises yield surface was used to describe the onset of plastic yielding. The elastic plastic simulations of the notched samples were carried out using the DD3IMP software, an implicit 3-dimensional finite element code developed at the University of Coimbra. At the notch region, an ultrafine mesh was created. Bending moments and torsion moments were applied by a single force. VT ratios were defined by changing the length of the prismatic portion. The loading orientation was defined by rotating the prismatic portion with respect to the y-axis. Let me show you some results about the multi-axial fatigue campaign. In this slide, we can see the typical surface crack paths and the initiation sites associated with the different loading histories. As expected, surface crack paths and initiation sites are significantly affected by both the BT ratio and the loading orientation. Briefly, surface crack curvature increases with higher shear stress levels and higher BT ratios. Regarding the initiation sites, they tend to be closer to the curved edge of the notch with the increase of the shear stress level and the angle. Both the surface crack trajectories and the crack initiation sites were successfully predicted from the first principal stress field and the maximum value of the first principal stress at the notch surface, respectively. Below, we can see the numerical predictions, and at the top, a comparison between the numerical simulations and the experimental observations. In fact, there is a very good agreement, which is an interesting outcome. Concerning the initiation angles, not surprisingly, they are affected by both the BT ratio and the loading orientation. These locations were also successfully predicted by accounting for the first principal direction at the initiation site. As exhibited in the figure, our predictions are very well correlated with the experimental observations. Maximum errors are lower than 5 degrees. The examination of fracture surfaces via scanning electron microscopy, as can be seen in the figures, has shown that crack initiation occurred from geometric irregularities or inclusions located at the notch surface. In addition, as expected for this alloy, we have found islands of inclusions and pores dispersed throughout the material. As far as the fatigue life prediction is concerned, as referred to above, the first step deals with the generation of the fatigue master curve. In this slide, we compare the stable hysteresis loops generated in the numerical simulations with those collected in the experiments for higher and lower strain amplitudes. We can clearly see that stimulations and experiments are quite close, which validates the proposed approach. Using the simulated hysteresis loops, we can calculate the total strain energy densities associated with different strain amplitudes. The corresponding numbers of cycles are estimated from the strain-life relationships defined from the two experimental tests. As can be seen in the figure below, the curve fitted using the mixed numerical experiment approach proposed here, which only considers two tests complemented by two numerical models, is similar to the one generated using a full experimental approach. The last step addresses the calculation of the total strain energy density at the notch root. The total strain energy density under multi-axial loading was calculated via the Alain's formulation using the elastic plastic numerical simulations. The typical energy distributions are plotted in the figure. Regardless of the loading scenario, the maximum values are close to the surface, and then the functions tend to asymptotic values. The effective energy was accounted for by applying the line method of the TCD. Finally, by inserting the effective energy into the fatigue master curve, we can estimate the fatigue crack initiation lifetime. Repeating the procedure for all cases, we can assess the predictability capabilities of our model. As can be seen in the figure, there is a very good agreement between the predicted lives and those determined experimentally, regardless of the BT ratio and loading orientation, which is an interesting outcome. Finally, a few conclusions. Fatigue master curves defined in terms of total strain energy density versus number of cycles to failure can be defined via two elastic plastic finite element models and two strain control low cycle fatigue tests performed using smooth samples. Crack initiation sites, crack initiation angles, and surface crack paths can be predicted from the maximum value of first principal stress, first principal direction, and first principal stress field at the notch surface, respectively. The effective value of the total strain energy density evaluated nearby the initiation sites using the line method of the TCD is adequate to correlate the fatigue lifetime with the applied loading for the notched geometries and loading scenarios investigated here. Thank you.